Thank you. So, hope you guys had a nice lunch. Okay, we'll start now. So, let me start by a simple question. Have you ever encountered a query which was probably slow in your development setup? Sorry, which was fast in your development setup, but didn't scale so well in production? If that's the case, then this talk will be of interest to you. So, I'm Nitin, and with me I have Mohit, and today we'll be talking about AEM search and how you can say goodbye to those slow queries. So, you might already remember us from the talk yesterday, but just a quick reintroduction. Both of us are developers at Adobe and JackRabbitO committers, and we've been part of the search and indexing team for almost 5 years now. So, let's begin. Okay, so here's a brief outline of today's talk. First, we'll start with some indexing and search overview. We'll talk about different types of indexings and a special focus on query engine. Then we'll talk about some common search problems. This we've curated from our experience while working on customer reported issues in the search area on AEM. Then we'll talk about some toolings inside and outside of AEM which can actually help you, debug any issues around indexing. And after having set up this context, we'll move on to the main part of the talk, that is slow query detection and analysis. I have a pretty good flowchart over here that will be helpful to see if a query can scale well or not. Then we have divided the different types of queries into 3 buckets: traversal, index traversal, and theoretically optimal queries. We'll see how to identify those, categorize them, and once you've identified one, what to actually do with it. And then we'll close with some key takeaways. Okay, I'll hand over to Mohit now for the initial sections.
Okay, so indexing and search overview. The first thing is we can divide indexing into majorly 2 buckets: sync indexing and async indexing. So as the name suggests, sync indexing is basically as soon as you write or update your content, it will be indexed. In async indexing, it basically works on the premises of eventual consistency, and a background job actually indexes the content in AEM. And RT indexes basically bridges the gap between these 2 indexes for the async indexes. It gives you a near real-time experience for your search queries. So, query engine. So, as soon as you execute a query, the first thing query engine does is it figures out what index it should pick, what's the best index which should be used for returning the results for this query. It calculates, estimates some cost for different indexes and figures out, okay, this is the best index we can use. If there is no index to return the results, in that case, query engine executes the query on its own and do a traversal on the node store to give you the results. In some cases, there are cases where your query constraints are not exactly handled by the index. In those cases, query engine picks the index, get the results from that index, and the rest of the constraints are then handled by the query engine. It traverses your results, which are coming from the index, and the constraints, it evaluates the constraints and finally gives you the results. For example, let's say let's say the index is not ordered, it doesn't have the ordered property for a particular property. The query, when executes, you will get jumbled up results, and query engine will finally sort those in the memory and finally give you the results. Another major task it performs is ACL evaluation. So ACL evaluation is not part of indexing. It works as a filter later on when results come from the index. Okay, so now we'll have a look at common search problems. We can basically categorize problems into 2. One is your query is slow, and the other one is query is not returning expected results. In case of slowness in the query, it's majorly if, let's say, we didn't find any index, it has to then traverse. It basically belongs to traversal queries, where you have to where the query has to be the results are coming by traversal of the node store. Then we have suboptimal index traversal queries, where your query or maybe the index are not optimal enough to give you the results, and which then query engine has to finally filter out to return the results. And then third category is where you are reading too many results. For example, if you have the query and index are optimal, but even in that case, the result set is too huge. And because of the hugeness of the content, the query becomes slow. Another bucket that I was talking about is query not returning expected results. It's something, it basically happens if your indexing, async indexing, the background job that runs is lagging behind. So in that case, you will get older results, though the content is now updated. Another problem, it can also happen if your index is corrupt or in case the query in itself is not correct. So we'll talk about some tools which we can use to diagnose the problems in indexing and your search. And the first tool is query performance tool. It's a really good tool. It tells you about the mechanics, how your query is being broken down to get results from the index. So it tells you about which index is going to be used, any alternate indexes, if are available, which can be used for the same query. It also tells you the query plan. So what constraints are being handled by the index and what are not. Then we have one cost estimation, which is used to figure out which index it should be, which this query should pick so that you can get results in minimum time. So this query engine, this query performance tool can be accessed via the URL mentioned on the slide for 6.5. And for AEM as a cloud service, you can access it via developer console. On the same tool itself, there's another tab, slow query tab, which basically lists all your queries which are slow. And information on that means how many reads are happening, how much are filtered, though that information is also available on the page. Please mind that this UI may change for 6.5 and AEM as a cloud service. So, but you get a gist of which queries you should pick and what alternates or query index changes are required for those queries. Okay, so there are some JMX statistics which we can use to figure out to get to know about the indexes and the queries, what's happening in the background. So one statistic is async lane statistics. It's basically gives you information about the background job that runs for indexing the content. Here you can get the information like what's the frequency of this job which is being run. Are there any failing indexes? When was the last time the job actually completed? Another statistic which is available on JMX is leucine index statistics. It tells you about what's the index size of the leucine indexes, number of documents indexed in that particular index, and also tells you about any corrupt indexes if available. What was the last failure that happened? It is also available on the JMX. This UI is present on 6.5, but in AEM as a cloud service, this is not accessible directly. But information like corrupt index details and these and error failures, those you can fetch from the logs in AEM ACS. So the last tool I'm going to discuss is OK Index Definition Generator. This tool is not present on AEM. It basically gives you index definition as soon as if you provide a query to it. So if you write a query, it will generate index definition, which you can use in the AEM to create your index definitions. So I'll pass it to Nitin for the next section.
Okay, so now we'll talk about slow query detection and analysis. Okay, so much before a query actually reaches a state where it'll start getting timed out, you'll see such logs. There are a couple of different snippets over here. In the first one, I have logs which are from a traversing cursor. Basically, it indicates that the query is not picking up any index and doing a repo traversal. And the second one is index traversed, which means that it is picking up an index, but it's not an optimal usage and it still needs to traverse the result set. These logs start popping up when the traversal starts hitting 10,000 nodes. and the query times out by default at 100,000 nodes. It's a configurable limit. Now, what's our plan is to actually prevent these logs from ever coming into production. So for that, I have this a bit complicated diagram over here. Let me just zoom it a bit. No, yeah, it's better. So the idea is to analyze the queries early on in the development cycle so that we can figure out if they'll scale well in production or not. And this flowchart can help doing exactly just that. So once I have a query, I'll just pass it through the explain tool, which Mohit explained, and it has a lot of information. The first thing that we need to check is whether it's using an index or not. If it's not using any index, then we need to check if there are any other alternative indexes in the system available that can actually serve this query in theory, but somehow they are not getting picked up. We can get these details from the logs of the explain tool. Then, if that is the case, then we need to analyze why the index is not getting picked up. There could be a couple of scenarios over here. First is your incorrect cost estimation. That is somehow the Traversal is looking more lucrative to the query engine than actually using an index, probably a bug somewhere. In this case, we can always make the queries use a specific index using the options index tag. Even if it is not an issue, I would still recommend that for any custom queries, we should use an index tag so that it uses a given index consistently. Okay. The second case could be the index is actually corrupt. In this case, this will get ignored from serving any queries. And what we can do over here is we first need to analyze why the index is actually corrupt. The JMX stats, etc., the toolings that we mentioned earlier, they can come in quite handy to do this analysis. And then once we fix the underlying cause, we would need to reindex the index. Okay. So tracing back, in case there is no other alternative index, then the solution is to create a new one. Now, if the query is actually using an index, then we need to check if the usage is actually optimal or not. By optimal, it would be that the index is actually serving all the constraints in the query. If that is the case, but still the query is slow, then we need to see if we are reading a very large result set. If that's the case, then we should consider pagination in our queries. We'll cover this in a lot more detail in a later slide. If that's not the case, then we should probably explore some other causes. There could be a lot of ACL evaluations happening, or there could be some problems in the underlying persistence layer, and the overall reads could be slow. The last scenario that we need to check is if the index that is getting picked up is not an optimal one. Then again, we need to check if there is any other alternative available, and if yes, then why it is not getting picked up, the same flow over here. But if there is no alternative available, then we need to analyze the query restrictions that are not being served by this index. And when we are trying to tune any queries, tune any performance for our queries, the first thing that we should try is to change the query. If we can somehow modify the query while still meeting the business requirements, so that it starts picking an index, available index optimally as is, then that is the best case scenario. However, if that's just not possible, then the last resort would be to modify the index to accommodate the restrictions that are not being served. Okay, with that, I'll close up this diagram and move on. Okay, so before I actually move on to specific examples of flow queries, I'd like to talk a bit about reindexing. In the last slide, I was laying stress on why we should actually try and change our queries first whenever we talk about optimization. That's because if we change an index definition in such a way that it changes how the content is being indexed, then a reindex is always required, and reindexing can be a costly affair, especially on repos with large content. Anyhow, there are a couple of ways to reindex online and offline. In the online reindexing, we basically make the changes to the index definition on a running AEM instance and then set reindex is equal to true, and then let the async indexing take care of the reindexing. However, this is really not recommended, especially for indexes that actually index the whole repository, and the repository has a lot of content, because this can put a lot of load on the running AEM instance. The other alternative is the offline reindexing. Now, there are a couple of ways we could trigger offline reindexing depending upon what flavor of AEM we are using. On 6.5, it runs via the Oak Run utility, and on AEM as a cloud service, it runs via the deployment pipeline. But either way, what is common in both is that it is a costly operation. For 6.5, it could require a downtime, and for AEM as a cloud service, it could require very large long running deployment pipeline. So, cutting the long story short, it is always advisable, and I cannot lay more stress on this, that we should always try and optimize our queries early on in the development cycle, because it is way much easier to accommodate for any index changes early on, rather than having to do that later on in the production environment where the cost can be really high. Okay, so now we'll be talking about some very specific examples, and for those, we've configured a simple index on the system. It indexes all the nodes of type NT-base. It has a couple of property restrictions on foo1 and foo2. By the way, there was a question yesterday around how to handle property indexing in AEM as a cloud service, so we could do something similar. Then foo2 over here has also an ordered set is equal to true, so we could actually do ordering on foo2. So in the first section, we'll cover traversal queries. These are basically the queries that do not use an index. So the first example over here, I have this query select star from NT-base where foo3 is equal to bar. And looking at the query explain output, I can easily see that there are no indexes used. And then we need to analyze these logs and see that there is no other alternative also available that might be getting ignored. So the solution over here is to create a new index or append this property to an existing index. So since I know that I already have an index on NT-base, so I'll simply add a foo3 property restriction to that index, and this would require reindexing then. Now, there could be a second scenario as well, where there is no index being used, but if you look at the query explain tool, you'll see something like this, ignoring the index adaptTo, which is not working correctly. So this indicates that there is an index present in the system, but it is not being picked up for this query because most probably it is a corrupt index. For example, there could be cases that the index was not able to connect to the data store for a continued period of time and was marked corrupt. So in this, we would need to dig up the logs a bit, find out the root of corruption, and then fix that, and then a reindexing would be required for it to be usable again. Okay, moving on. This is probably more... Okay. Okay, sorry. So this is probably a more interesting type of problem to solve. These are the index traversal queries. These actually use an index, but not optimally. So when would I say that a query is optimal? I can broadly divide my query into these 4 parts: node type restriction, property restriction, path restriction, and sorting. And if my index is able to serve all the constraints of a query, then we say that it is the optimal index for the query. However, if that's not the case, then whatever constraints the index does not serve are then handled by the query engine later on in memory, which could make the query difficult to scale. Okay, so now how to check whether a query is using an index optimally or not? We've already gone through the explain tool bit in the previous slides. Now we'll talk about a specific part of it, that is the execution plan. So for example, I have a query over here which has 2 restrictions, foo1 is equal to bar and foo3 is equal to bar 3. However, looking at the execution plan, I see the Lucene query over here is only mentioning foo1 is equal to bar 1, which indicates that the restriction on foo3 is not being handled by the Lucene index and will be taken care of by query engine, and thus this is not an optimal query. So the second example over here is we have a property restriction on foo1 and a path restriction on /content, and as we can see, the path restrictions get translated into this plus ancestors query on the Lucene index, and we can see that it is an optimal query. Both the restrictions are being handled by the index. And then on this slide, I have a couple of queries. On the left-hand side, it shows how the execution plan looks when the sort order is actually handled by the index versus when the sort order is not handled by the index. Okay, moving on. So I'll talk about a specific example now. We have a query foo1 is equal to bar ordering by foo1. But as I can see in the execution plan, the ordering is not being handled by the index. What are the potential solutions? As I mentioned earlier, we should first try to change the query. So I already know that I have a property called foo2, which is already ordered. So could I do that? If I change the query, I can just run through the explain tool and see that, okay, it works. But if my business requirement is as such that I only need to index by order by foo1, then I'll just need to add this ordered is equal to true on the foo1 property and then reindex, and things would work well then. Okay. Now, the second example I have over here has a couple of property restrictions on foo1 and foo3, but as we can see in the Lucene query over here, only one of them is being served by the index. Now, this could be a very slow query potentially, especially if we have a lot of nodes where foo1 is equal to bar matches. I'll just show that in an example on the next slide. What the solution to this is that we would need to add foo3 property restriction on this index so that it can serve both the property restrictions. So just talking about an example where such queries can be very slow. Consider that I have 100,000 nodes in the repository, and out of those, 10,000 nodes have foo1 is equal to bar, but only 2 out of these have foo3 is equal to bar 3. Now, to serve the query over here, the index would actually return me 10,000 nodes, and then the query engine will need to scan all these to give me a result set of just 2 nodes. So imagine how slow that can be. So hence, we need to do the analysis via that flowchart and figure out if my query can scale well or not. Okay, so with that, I'll hand over to Mohit to take care of the last section.
Okay, so Nitin had mentioned how you can optimize or your indexes, query and indexes, and how they impact the query solutions, whether they means how to make them fast. But there are cases where even though you have both your query as well as your index, means all the constraints are being handled properly, even in that case, there can be slowness. And the main reason for that is the result set is like too huge. Let's take an example. Let's say we have select star from empty base where foo1 is equal to bar 1. In this, the query explain tool mentions that the number of nodes in the results are 10,000 plus. So whenever you try to execute this, it will have to fetch all the results, 10,000 results, which will make it slow. And as I mentioned, if your query is optimal, you don't have any other use case. The only solution to this problem is pagination. So we will be discussing 2 types of pagination here: limit offset and key set pagination. First, we talk about limit offset pagination. So the query that we had, if we change the query and add this option offset 0 limit 10, it basically constrains your query and it just returns 10 results. So let's take an example. We have a website where you want to show 10 results on first page and next 10 on the second page. So if you change the query from empty base where foo1 is equal to bar 1 and add this option limit offset 0 limit 10, you will get first 10 results for your first page. If the user then enters the second page, you again can execute the query with offset 10 and limit 10, and with this you will be getting the next 10 results. Keep in mind that offset and limit means even if you add option offset 10 limit 10, you are basically traversing 20 results and filtering out first 10 results to give you the next 10 results. So even in this case, let's say you have infinite scroll set up on your page. In that case, if someone is like scrolling, you will eventually hit 10,000 traversal warning. And on each scroll, you will find that the query is getting slower and slower because you have to filter out all the results which are coming previously, and you just want the next 10 results. So this is one limitation with offset limit pagination, limit offset pagination. So The next pagination strategy we have is key set pagination. This is what we usually say that you should go with this if your use case is handled by this. But it's a little complicated to implement, and there are some prerequisites to enable this. So the thing is, means you should have a property here on which you can order, and where you can actually do a C query. So these are like two things which you should have to implement key set pagination for your query. So let's take an example. So the query that we had, select star from empty base where foo1 is equal to bar1. So the key that I was mentioning, which should be ordered, let's say that is JCR last modified, and it is an ordered property. So you can modify the original query to a key set paginated query where we are basically setting JCR modified is greater than some timestamp, and you are ordering by JCR last modified. In this also, we also added this limit offset so that you just get the first 10 results. Now, as soon as you get these 10 results and you want to go to second page, the change you have to do in your query is change the timestamp here with the timestamp of the last element, which was coming from your previous query. So it's basically a chaining which is happening. You're getting the results in the first 10 results, then next 10 results, and to get the next 10 results, you basically change your timestamp there to go on. And in this way, as you are getting all the results, you are basically seeking the result. You are not traversing or filtering the results. So this you won't hit the traversal limit here. Everything is basically getting returned from your query itself using the index. So that is all for the key set pagination. Next problem that we face is are the cases, because as I mentioned previously, ACL evaluation happens outside of your queries, means indexing, it has to be filtered out at later stage once you get all the results. So these kind of problems can happen at later stage. Once, means your index is optimal, your query is optimal, but even in that case, your query is slow. So the only solution to this is you should better structure your content so that the ACL evaluation do not filter too many of your results. You can add path restrictions here. So content manipulation is the only way to get rid of ACL checks if you hit this particular problem. And it's a little complicated to figure out because this will happen for a subset of users. So for a user, it may work fine, but for another user, the same query may fail because of ACL evaluation happening. So a great example to showcase ACL evaluation issues is your faceted query. So because of the problem of ACL evaluation happening at later stages, which makes your facet queries really, really slow, we actually have few configurations in the index definition itself so that you can figure out, means you have to define what kind of ACL evaluation you want for your results. So the three types of configurations are: you can set your facets to secure, insecure, or statistical. With secure config, it basically says you have to do ACL evaluation on your complete set. If you set this configuration to insecure, in that case, no ACL evaluation happens, and you get results what is there on the index itself. Then there is this third option, statistical, where basically we get a random sample set, we calculate ACLs, and finally we set it or extrapolate that on the complete repository to get the faceted results. So in this case, you have to make sure what exactly you want from your queries and which particular config is best for you. So in case of facet query, make sure to set a proper configuration. With this, we conclude this talk. Some major takeaways from this presentation are: you should always analyze your query first early in the development cycle. You should always try to tune the queries first. The more the restrictions, the better, because later on, if you try to include more restrictions, you will face problems. You may even have to reindex. And the third thing is, changes to index definition should be your last resort, especially in the production environments where content is like huge and For some of the on-prem customers, it can even run for days. Okay, so we'll also be part of Meet the Expert session. If you have any queries, please reach out to us. And for now, go make your queries fast. Thank you.
So before I go and fix all my queries because they're super slow, I have some questions for you. Yeah. What's, in your opinion, the best solution or approach when we do query reading of like more than 20,000 nodes?
So this we covered in the presentation. So the key set pagination is something you should really look at because that's the only way where you are not filtering the result. The main problem is filtering out the results. If you can skip that, most of the things you can get from the index itself.
Okay, AEM as a cloud service uses MongoDB as persistent backend. Locally and with the RDEs or even 6.5 on AMS, on-prem, and so on, this is different. What are your recommendation index tuning specific to the persistent backend?
Okay, so it doesn't really matter because the indexing in AEM is actually handled by Lucene indexes. So it doesn't really matter if you're doing it on MongoMK or TarMK. We're not using the Mongo's index for the JCR queries. So it's agnostic of the persistence layer that is running underneath.
Why does Oak index CQ page Lucene in AEM as a cloud service only consider properties up to 4 levels aggregation? That index is even used for incoming references rails in AEM 6.5.
Yeah, so I think so. This is something the sites team might be able to answer better because they are owning the index definition for that and the use case from a solution standpoint. I don't think so. We are at a position to answer this.
All right. Last one. Is it possible to return query results directly from the indexes without touching other parts of the repository?
Yeah. So basically, if you are, as Mohit mentioned, right, if all the restrictions are being handled by the index itself, you would get all the results from the index. Basically, the index would return you the paths of the nodes. But to read those nodes, then you would actually need to hit the repository to get the node content finally. That needs to be done. But at least if you want to get the paths, that can be figured out from the index as long as all the restrictions in the query are being served by the index directly.
So they're like, you can skip few things, but the query engine, right? That's the main component here, which is basically helping you analyze everything and finally give you the results. So ACL evaluation and those things are part of it. You can't skip that. But if you are just interested in the results, what are you are getting, there is this query builder. You can use that. Though ACL evaluation will happen, but if you have right constraints where you are not filtering too much of the results, you can get right responses. And the other one is your this query explain tool, right? There also you get the results. It also tell you explain the query explanation and all. So these two tools you can use to initially figure out what are the problems and what the count of the results and all those things. You can get that directly.
Thank you. Nitin and Mohit, they came all the way from India here on stage. Big applause. Thanks a lot.
Thank you.